Welcome back. In the first part of our conversation, we explored how your curiosity about software infrastructure eventually led you into cloud and edge systems engineering. Now, I'd like to ask something that many learners wonder about. What is the reality of working in cloud and edge systems that textbooks don't prepare you for?
That's a great question. Many people think cloud and edge systems engineering is simply about launching virtual machines or deploying applications to the cloud. The reality is much broader. Your job isn't just to keep systems running, it's to design platforms that remain reliable, secure, scalable, and responsive under constantly changing conditions. The cloud is only one part of the system, the edge is another. Networks connect them, applications run across them, data continuously flows between them. Your responsibility is making sure all those pieces work together seamlessly.
So, it's much more than managing servers.
Exactly. Modern cloud engineers spend less time thinking about individual servers and more time thinking about entire systems. Instead of asking, is this server working? We ask, can this application continue operating if an entire data center becomes unavailable? That's a completely different way of thinking. It's called designing for resilience.
Many beginners hear terms like cloud computing and edge computing together. Could you explain the difference in a simple way?
Imagine a large public library. All the books are stored in one central location where anyone can access them. That's similar to cloud computing. Now imagine a small reading room inside your neighborhood that keeps only the books people use most often. You don't have to travel across the city every time you need one. That's edge computing. The cloud provides enormous computing power and centralized services. The edge processes data closer to where it's created. Together, they provide both scale and speed.
Why don't industries simply send every piece of data to the cloud? Wouldn't that be easier?
Sometimes it is. But many industrial applications can't afford delays. Imagine an automated production line inspecting thousands of products every minute. If every camera image had to travel to a distant cloud server before making a decision, defective products might already have moved further down the production line. Or imagine an autonomous vehicle waiting several seconds for cloud instructions before applying the brakes. That would be unacceptable. Edge computing allows critical decisions to happen immediately while the cloud handles long term storage, analytics, and coordination. That's why modern industries rely on both.
Another phrase that appears everywhere today is cloud native architecture. What exactly does that mean?
Think of building a city. Instead of constructing one enormous building that contains everything, you create many specialized buildings connected by roads. Each building has its own purpose. Cloud native architecture works in a similar way. Applications are divided into smaller independent services called microservices. One service might handle user authentication, another processes payments, another collects sensor data, another generates reports. Because they are independent, each service can be updated, scaled, or repaired without disrupting the entire application. That flexibility is one of the biggest advantages of cloud native systems.
That naturally brings us to containers and Kubernetes. People hear these terms constantly. Why are they so important?
Imagine moving your belongings every time you change apartments. If everything were packed differently each time, moving would be difficult. Shipping containers solved a similar problem in global transportation. They standardize how goods are packaged so they can move easily between ships, trains, and trucks. Software containers do the same thing. A container packages an application together with everything it needs to run. Whether it's deployed on a developer's laptop, a cloud platform, or an edge device, it behaves consistently. Kubernetes then acts like an intelligent logistics manager. It decides where containers should run, replaces failed ones automatically, scales applications during busy periods, and keeps the entire platform operating efficiently.
Many learners also hear about industrial IoT. How does it connect with cloud and edge systems?
Industrial IoT provides the data, cloud and edge platforms provide the intelligence, factories contain thousands of connected devices. Sensors measure temperature, vibration, pressure, energy consumption, and equipment health. Edge devices collect and process this information locally. Important events are sent immediately to operators. Meanwhile, cloud platforms store historical information, analyze trends, and support business wide decision making. Without industrial IoT, cloud and edge platforms would have little operational data to work with. Without cloud and edge infrastructure, industrial IoT data would remain isolated and underutilized.
Factories generate enormous amounts of information every second. How do engineers manage all that data?
That's where data pipelines and real time stream processing become essential. Imagine a city's water supply. Water travels through carefully designed pipelines from treatment plants to homes. Industrial data flows in a similar way. Sensors generate continuous streams of information. Data pipelines collect, organize, transform, and deliver that information to applications, dashboards, databases, AI systems, and analytics platforms. Real time stream processing allows organizations to analyze events the moment they occur instead of waiting until the end of the day. That enables faster operational decisions.
Security must be another major concern. How has cloud security evolved?
Cloud security has changed dramatically. Years ago, organizations assumed everything inside their corporate network could be trusted. Today, that assumption no longer works. Employees work remotely, applications run across multiple cloud providers, edge devices operate in factories, hospitals, and remote locations. That's why many organizations now follow zero trust architecture. The idea is simple. Never assume a user, device, or application is trustworthy simply because it's inside the network. Every request must be verified. Every connection must be authenticated. Every access decision should be continuously evaluated. Trust becomes something that's earned, not assumed.
We've talked about cloud, edge, IoT, and security. How do organizations keep all these systems updated without disrupting operations?
That's where DevOps, CI/CD, and infrastructure as code become incredibly valuable. Years ago, software releases happened only a few times each year. Today, organizations may deploy improvements several times every day. Continuous integration automatically checks whether new code works correctly. Continuous delivery automates testing and prepares software for deployment. Infrastructure as code allows engineers to define cloud infrastructure using version controlled code instead of manually configuring servers. Together, these practices make deployments faster, more reliable, and easier to reproduce.
Artificial intelligence is now appearing everywhere. How is it influencing cloud and edge systems?
AI is transforming how distributed systems operate. Traditionally, data was collected at the edge and analyzed later in the cloud. Today, many AI models run directly on edge devices. Imagine a camera inspecting products on a production line. Instead of sending every image to the cloud, the edge device performs AI inference immediately. Only important events or summarized information are transmitted to the cloud. This approach reduces latency, lowers bandwidth costs, improves privacy, and enables faster decision making. That's why AI at the edge is becoming one of the fastest growing areas in modern computing.
Organizations also talk about hybrid cloud, multi cloud, and digital twin platforms. Why are these becoming so popular?
Because no single environment solves every problem, some applications remain inside private data centers. Others run on public cloud platforms. Certain workloads execute on edge devices. Hybrid cloud connects private and public infrastructure. Multi cloud allows organizations to use services from multiple cloud providers. Digital twin platforms combine real time operational data with virtual representations of physical systems, helping engineers simulate, monitor, and optimize industrial operations before making changes in the real world. Together, these technologies provide flexibility, resilience, and better decision making.
Before we conclude this segment, if there is one lesson every future cloud and edge systems engineer should remember, what would it be?
Don't think of cloud computing, edge computing, Kubernetes, DevOps, security, AI, and data pipelines as isolated technologies. Think of them as parts of one intelligent ecosystem. Cloud provides scalability, edge provides speed, industrial IoT generates data, data pipelines move information, containers package applications, Kubernetes orchestrates them, DevOps keeps software evolving, Zero Trust protects everything. AI adds intelligence. Digital twins help organizations understand complex systems before making changes. When you understand how these pieces work together, modern distributed systems begin to make sense.